Hello, everyone. Really excited to be here and present our initial work on trying to answer this question. Can biomolecular structure predictors generalize to alternative conformations? Also, build on some of what Ellen talked about, so really glad I got to go after that talk. Great. So all of you in this room are aware that you can take a biomolecular sequence, feed it into AlphaFold or related structure prediction methods, and get a highly accurate set of atomic coordinates describing the structure of that molecule. However, this set of atomic coordinates is a single state. And to capture the full functionality of biomolecules, we need to model the full conformational ensemble, especially for events like binding and catalysis. So we have this problem where we need to capture the full conformational ensemble, and now that these models are generative, maybe we can try to bias them to sample from the ensemble. But as Ellen mentioned, we have this challenge in evaluating how well our models are actually capturing that underlying ensemble. One thing that in structural biology we have is the underlying data. The structural data in both X-ray crystallography and cryo-EM are ensemble averaged. In X-ray crystallography, we have a biased ensemble. It is limited by the crystal lattice, but there are still movements that are occurring there, and we're averaging spatially and temporally over the billions of molecules that are present in the protein crystal. We can then transform that data into a density map that retains the ensemble average. In cryo-EM, we have, as Ellen explained, in the pipeline, we computationally average over all of these low signal projections, and we get a density map that, again, represents the ensemble. We think that even though this ensemble averaging has been a computational experimental challenge in the past, here it presents an opportunity. What you're looking at here is an example where a manual modeler deposited two sets of atomic coordinates for a loop here. What's in gray is the density map from X-ray crystallography, and you can see atomic coordinates for both the closed and open states of this loop. These alternative conformations are deposited as alt locks in the PDB, and they're strictly stripped out of all the training pipelines for public structure prediction methods, and we think they provide a natural evaluation set for ensemble prediction. In this presentation, I'm going to focus on 4 specific proteins. Each are relevant in their own right. What's in the top left here is the protein phosphatase PTP1B. This loop opening and closing is important for catalysis and activation. This is a cancer and diabetes drug target. In gray, I'm showing the A alt lock, which is what models would have seen in their training data. And in color is the B alt lock, which has been stripped out. I'll focus a little bit more on 5-SOP and 1-VME, 2 of the proteins here. 5-SOP is from a fragment screen, and there's a low affinity fragment bound in the B alt lock. However, the processing pipelines for AlphaFold 3 and related methods, they sort of greedily select the ligand even though it's only in the A alt lock, but take the A conformation for the protein. So the underlying training data here has a wrong structure. The experimental data doesn't support the ligand being bound here. This is something that will be important to recognize as we go forward and evaluate these. 1-VME, I want to point out, this is an example where manual modelers had given up on producing these 2 sets of atomic coordinates because the density was too confusing. But an early version of an automated method that we developed in the lab called QFIT was able to automatically resolve these 2 conformations. And these methods like QFIT will be important for benchmarking and generating data for evaluating and training models in the future, I think. So no AlphaFold 3 like we tested was able to predict both alt locks with multiple seeds. Here again, I'm showing the A alt lock that they would have seen in gray for 6B8X, and in color is the alternative conformation. Different structure prediction methods we use predict different of these conformations, but they aren't able to capture both when we run them with multiple seeds, which is what ideally we would like them to do to capture the conformational ensemble. I'm just going to focus on the bolts predictions here. On the left, 5-SOP, we see it recapitulating the training structure where the fragment is stabilized in the alt lock A, not B. For 1-VME, we're not capturing either of these alt locks particularly well. And then for 4-OLE on the right, we see it's sort of leaning towards the A alt lock on the right, but is not capturing that helical turn. So natively, these structure prediction methods aren't capturing the conformational ensemble. What's a way we might be able to bias these models or augment them to predict all alt locks? Inspired by the work of people here in the audience, we implemented a guidance framework for Boltz 2, where we take density maps and generate ensembles from the model to fit the density maps during inference. So we're trying to sample from this distribution of ensembles given the density. How we specifically do this is using training-free guidance with the density maps. So we calculate from the alt locks I showed a synthetic map with equal occupancy in both the A and B alt lock. There are two conformations here. If you only predict one, you aren't going to be fitting this density well. We can then compare that with the calculated or the denoise prediction at a given diffusion step, calculate some loss, take a gradient step towards fitting the density better. And we apply this iteratively throughout the denoising trajectory. We also combine that guidance with the Feynman-Kotz steering framework. We do this on ensembles, so we have multiple ensembles as particles being resampled throughout the trajectory, and we saw this improved our results. So now to get into the results, in color, I'm always going to have the predicted ensemble from the model and guidance, and in gray are the deposited alt locks. And these structures I'm showing, the ensembles, will be from sort of our best cases across a grid search of our guidance parameters. For 6B8X, we do a really good job. I'm not showing the density here, but the underlying alt locks that generate the density, we're getting a super low RMSD to those two alt locks, so we're successfully able to bias the model to capture this conformational ensemble. However, for the other cases, we don't do as well. 1VME, we do a bit better job of capturing the A alt lock, but the B is missing. For 4LAE, we do get that helical turn, but neither of these alt locks are being captured as well as they were for 6B8X. Importantly, the fragment-bound case, we aren't able to guide the model to sample this conformation. And this reflects a bias where the ligand was bound in the loop in phenylalanine in conformation. And we think that this reflects a sort of mistake in the prior that's going to be really important to correct going forward as these models are being applied to things like virtual screening. We think that with this, we wanted to dig a little bit deeper and see why we did so well on 6B8X. When we look at the training set, both conformations of 6B8X, both that open and closed conformation, are well represented. The training cluster size for 6B8X is relatively larger compared to the other proteins that we tested. And when we quantify the conformational change that we are looking at here by taking the distance from the catalytic cysteine to the alpha carbon of that phenylalanine in the loop, you can see that when we calculate the histograms of these distances in a subset of the training cluster greater than or equal to 80% sequence identity, we see that when we calculate the histogram with alt locks and without alt locks, these are overlapping very, very well. So we're sort of, both of these conformations are well represented in that training set. For the other examples, this is not the case. 1VME only has 4 structures in its training cluster, and 2 of those, the primary conformation that would have been seen was the A conformation. In 2, it would have been the B conformation. And then for 5SOP, all of the structures in the training set strip out that B-like conformation. So to us, this indicates that we really need to move beyond the single sequence to single structure paradigm for training structure prediction methods. We could potentially use the synthetic data from different modalities, whether it's from generating ensembles based on the underlying experimental data here, or using alt locks, or using MD data. We really need to move beyond this paradigm. So with that, I wanted to sort of give a little bit further discussion. I think what I'm really excited about in the field is that we have a lot of experimental data that we're actually leaving on the table in the PDB. We have density maps and we have a lot of this information that we can incorporate into structure prediction methods during inference to produce ensembles that fit the data better. We can evaluate those against held out sets of that underlying experimental data, and we can combine multiple sources of experimental data potentially to then augment these methods, and we can use synthetic data from this process to train new models that cover more conformational space and hopefully set up a sort of flywheel so that we can iteratively improve the modeling that we're doing. I'll hint that I'm really excited to be continuing building out infrastructure for this as a part of the Diffuse project, and I'd really love to discuss this more with you all later. And with that, I'll thank my lab, the Fraser Lab, For all the support, I'll thank Henry Vandenbedem for feedback and mentorship, and also Stephanie Vinkovich, who's here, also Fraser Lab alum and a part of the Diffuse project. Our code is out on GitHub at fraserlab/EDG, and with that, I'll take any questions.
You mentioned, oh, here we go, thank you, 2FO minus FC maps that you are taking from the CIF or the MTZs from PDB, right?
So I'll clarify, in this, we're using synthetic density generated from those all locks. Ideally, in the future, you might use something like a 2FO minus FC, but of course that requires an initial model for phases.
That's my question. Yeah, so you have to be very careful, right? Because those maps will have model bias.
Yes.
Unless they're experimentally phased maps, but there's not many of those around.
Yeah.
And then the other thing you have to be careful of is before 1994, we had no cross-validation, so no R-free, which means the bias is really bad.
Yeah.
And so I agree with you. There's a ton of stuff in the PDB that's, as you say, left on the table. Just be very careful about the quality and when those data sets were measured and, the model bias. And also you've got non-crystallographic symmetry. But there's a few things you can do. You can do things like simulated annealing emit map calculation. So you shake out bias with a little simulated annealing. And I think your approach could be really powerful if you were to do that and to really utilize that data to get the best sort of dynamical data out there you can.
Yeah, we're definitely interested in doing a bit more interesting map processing during this inverse procedure, like, calculating, or using our model sort of Anyway, I guess there are a lot of opportunities for doing creative map processing to get out that bias, and of course we'll be filtering out a lot of that early data because again, there are a lot of cases where experimental data wasn't even deposited, so we need to be careful of that too.
Thank you.
Very interesting talk. So I guess my first question is so since you use analogs to calculate the density, so is that totally differentiable since you use that for the conditional guidance for the boards too?
Correct, yeah. So generally the refinement algorithms out there have implemented ways of computing the density in real space, and we ported that over to PyTorch and made it differentiable.
Yeah, and the second question is I noticed the structure you calculate from the density does not have hydrogen there. So I'm not familiar with cryo-EM. Is it important to just exclude hydrogen from these structures?
Yeah, so I think at high enough resolution, especially in X-ray crystallography, hydrogens can matter. But I think in our case, we're not yet at that point where we're generating models with this that we are really going to be improving our models a lot by including hydrogens. You can also, in your map calculation, sort of add writing hydrogens to improve, how you're fitting that. So there are some additional parameters you can use there. But yeah, in our cases, we're not at sufficient resolution. The hydrogens are really going to be really visible to us.
Thank you.
Thank you.